JC Tuition, and today we're going to talk about enthalpy. This is sort of an intro to understand the basic concepts of enthalpy. Um, I feel like this is quite important to understand before you start making calculations. So that's sort of what we're going to be going through in this video. So what is enthalpy? So enthalpy is measured. So enthalpy is denoted by the letter H, and it's a measure of the heat energy in a chemical system. So H for heat, if you'd like. When I talk about a chemical system, I'm referring to sort of atoms, molecules, ions making up the chemical. So imagine I just drew a flask in here and there's some contents in it. Well, this is the system, sort of what's making up the contents of the flask. Okay, I'll label that system. Enthalpy can sometimes be thought as the energy stored within bonds. So, such as between oxygen molecules. But then enthalpy alone can't be measured, but enthalpy changes can. So sometimes you can see this delta, which just means change in enthalpy. We can measure that. We know that in a chemical reaction, we have our reactants and our products, and they're likely to have different enthalpies. And the difference in enthalpy change can be measured, as I said, and that's with the formula, the enthalpy of the products. I'll just write products, take away the enthalpy of the reactants. And enthalpy can be positive, it can also be a negative number. It depends whether the products contain more or less energy. If the products contains more energy than the reactants, then obviously it's going to be positive, and vice versa if the reactants contain more energy. Just a quick reminder, the law of conservation of energy you should be familiar with. It's a fundamental rule of science and states that energy cannot be created or destroyed. All right, and it's quite important because let's go back to this box here. You're probably wondering what this is here for. So we have our system, which is the chemicals, the reactants, and our products. Fine. The surrounding is our apparatus, if you like. So that's the surrounding. So it's the actual apparatus, and maybe there's a thermometer in there. I'll draw a thermometer actually. I feel like that would be useful. Okay, and the universe, right? The universe is everything. The universe is the whole box, if you like. The universe is our surrounding plus the system. So like I said, enthalpy can't be measured, but enthalpy change can be measured, and we measure that by the energy transfer between the system and its surroundings. So let's say energy is coming from the system to the surroundings, so this way. Well, that is called an exothermic reaction. So from the system to the surroundings, we call that an exothermic reaction. All right, exo. And the other way around, from the surroundings to the system, so this way, that's an endothermic reaction. So what's sort of exactly happening in an exothermic reaction? Well, the chemical system's releasing heat to its surroundings. So because of the law of conservation of energy, any energy loss by the chemical system is balanced by energy gain to the surroundings. Yeah. And because our reactants are losing energy, because we're losing energy, enthalpy change is negative, so that will be negative. And because energy is being transferred to the surroundings, you'll see this thermometer go up. The temperature of the surrounding increases as it's gaining energy. Yeah. Same is true for an endothermic reaction, so where energy is transferred from the surroundings into the system. So the chemical system takes in heat energy from the surroundings. So any energy gain, again, law of conservation of energy, any energy gain in the chemical system is balanced by the same sort of energy loss by the surroundings. Enthalpy, this time, the change in enthalpy, therefore, because there's a change in energy, is positive. And because the surrounding is losing energy to the system, you'll see this temperature scale will be dropping as we are losing energy. Onto a graph, what we've sort of been talking about. So these, what I'm about to draw, are called enthalpy profile diagrams, and we'll draw this for exothermic reactions, and we'll also do it for endothermic reactions, so you can sort of get a taste of what they look like. Right, so for exothermic, we start off with our products. Yep. You know what, screw it, I'll write out a whole chemical equation. Let's do magnesium reacting with oxygen. Right, it's good practice to put their states in. So oxygen a gas, magnesium a solid, and So that's our products, if you like. So this is where we write our products, and it as the reaction goes on. So the progress reaction goes on. Well, we have our reactants, and we know, as we spoke about in the last page, the reactants have lower enthalpy because we know the enthalpy change is negative in an exothermic reaction as energy is being lost to the surroundings. Yeah. So this forms, well, magnesium oxide, and I'll just balance that like so. Okay, so as I was saying, enthalpy change you can actually denote on the diagram. You can see it's enthalpy is going down, enthalpy is negative. That's fine. What else can we put on this? Well, we can put activation energy. So what is activation energy? So as we know, atoms and ions are sort of held together by chemical bonds, right? And during chemical reactions, the bonds and the reactants need to be broken by an input of energy to break those bonds, and then new bonds are formed. Yeah, that's basically what a chemical reaction is. And the energy input we need to put in to break those bonds acts basically as an energy barrier to the reaction actually occurring. So we need this bit of energy, and this energy is called activation energy. It's the minimum energy required for a reaction to take place. Okay, and so this is the energy we need to form. So you put a curvy line like this. You have to draw a dotted line across. This energy here is the activation energy. It's energy going into the system to break the bonds to let the chemical reaction take place. And we denote this by EA for activation energy. If a reaction had a small activation energy, so imagine instead it curved to about here, then our activation energy would only be this dotted line here. Well, these reactions take place really quickly because the energy needed to break the bonds is sort of readily available from the surroundings. Whereas very large activation energies, they present a very large barrier to the reaction actually occurring, and they might take place very slowly if they occur at all. Anyway, let's also draw one for endothermic reactions. So this time we know enthalpy change is positive. So we start off with our reactants down here. An example for an endothermic reaction is nitrogen, nitrogen gas and oxygen reacting, right? Like I said, we know that enthalpy change will be positive, as discussed in the last page. And we form our products, and our product is nitric oxide. Of course, just need to balance that. And for this one, the activation energy, exactly the same thing. Energy needs to be put in to make the reaction happen, and that is always up to the peak, basically, the activation energy. All right. A lot of definitions and stuff you sort of need to know for enthalpy change. It's quite wordy, and I feel like understanding the definitions is really key before you sort of move on and make calculations. So we've got the first definition here, which is the standard enthalpy change for reaction is the enthalpy change that accompanies a reaction in the molar quantities shown in a chemical equation under standard conditions with all reactants and products in their standard states. Well, what are these standard conditions and standard states? What does that mean? Well, if we're talking about enthalpy change, so that's enthalpy change, and we say we're in standard states by this symbol here, right? And we're referring basically a reaction that occurs under standard conditions. So these standard conditions are standard pressure. I'll write these down for you, which is 100 kilopascals, very close to the atmospheric pressure of 101 kilopascals. But this is the standard pressure we use. Temperature has to be also standardized, and the temperature we use is 298 Kelvin, which I guess in lay terms is 25 degrees Celsius, just minus 273. Standard concentration, and what we use is 1 mole per decimeter cubed. This is of course only relevant to solutions. And a standard state, and that's the physical state of a substance under these standard conditions. So in 100 kilopascals and 298 kelvins. All right. So now that we understand what that is, let's think about what the standard enthalpy change for reaction is. So it needs to be under standard conditions with reactants and products in the standard states. Fine. The actual enthalpy change, the rest of the definition, we've got enthalpy change that accompanies a reaction in the molar quantities shown in the chemical equation. So it just depends on what the chemical equation shows. So for instance, here we've got magnesium and oxygen. Forms magnesium oxide, and we can balance this, right? Well, we've obviously got 2 oxygens on the left, 1 on the right, so let's balance it. So we've got half. There you go. So now we've got 1 mole of magnesium. Well, now we've got half a mole of oxygen and 1 mole magnesium oxide, and the enthalpy change standard enthalpy change reaction, which we denote with the change R for reaction, and then enthalpy, and we obviously say that is standardized. Well, this is minus 602 kilojoules. So kilojoules, this is how we measure energy, obviously, and that's per mole. But let's suppose, I'm just going to rub this out. Let's suppose we balanced it a bit differently. Instead of using fractions, let's say instead we just said, okay, that's fine. If there's two oxygens to the left, we'll say 2 oxygens on the right, and just put a 2 in front of the magnesium as well. Well, now we've got 2 moles of magnesium, 1 mole of oxygen, and 2 moles of magnesium oxide. What do you think the enthalpy change of reaction is? Well, what's happening here is, well, like it says here, it's the enthalpy change that comes to reaction in the molar quantity shown in the chemical equations. Well, because our moles have doubled, well, our enthalpy change doubled. So last time it was what, minus 62, so it must be minus 1204, and the units kilojoules per mole. Yeah, negative because it's exothermic, but that is what the standard enthalpy change of reaction is. The next definition is the standard enthalpy change of formation. So last time we did of reaction, now we're doing formation. So it's the enthalpy change that takes place when 1 mole of a compound is formed from its elements under standard conditions with all reactants and products in the standard state. So we sort of talked about the last part of the definition, and that applies here as well. Well, let's use this example again of magnesium and oxygen forming magnesium oxide. Well, let's think about the definition saying. So we're saying we're forming 1 mole of a compound from its elements. So that means we can only form a mole of magnesium oxide. So we need to balance it so that only 1 mole is formed, right? So the only way to do this is we can't change this right-hand side because that will increase the moles, so we can only just half the oxygen, yeah, because that's the key part of the definition, and that's basically all it means. We can't balance it using whole numbers this time because then it wouldn't match the definition of forming only 1 mole of magnesium oxide. Enthalpy change of formation, well, it's by this triangle. Instead of the R, we now put the F, so you're very creative, and then the rest is the same, and it's the same enthalpy change that we used in the first time round of 602 kilojoules per mole. Standard enthalpy change when combustion occurs. So this is where the enthalpy change that takes place when 1 mole of a substance reacts completely with oxygen under standard conditions with all reactants and products in the standard states, blah blah blah. So that means we need to start off with 1 mole of a substance, and we can't change that. So let's do butane, right? So we've got 1 mole of it, and I cannot put a 2 in front of this. Just consider this for the rest of the what I'm about to do. I cannot put 2 in front of this because that will make it 2 moles of it. We can only have 1 mole of it. That is what the definition says. All right. So let's carry on. So it reacts completely with oxygen, also a gas. So we're putting in. I should have said this earlier. Actually, we're putting in the state symbols because to show that they're in their standard states. It's important for the definition. When anything combusts, we know the combustion products are CO2 and water. Yeah. Now let's have a go at balancing this. So on the left we have 4 carbons. On the right we have 1, so that's 4. We've got 10 hydrogens on the left, so this must be multiplied by 5. Now we have 13 oxygens, so we need 6.5 of these, right? So we have to use fractions here because we can't go around making this a quarter or whatever, because then it would not fit the definition. The fact that we need 1 mole of the substance, butane, yeah, and that's basically standard enthalpy change of combustion. The enthalpy change of neutralization, and this is where we measure the energy change that accompanies a reaction when an acid reacts with a base to form 1 mole of H2O liquid, water, under standard conditions with all reactants and products in their standard states. So example is where we use hydrochloric acid, sodium hydroxide, so an acid and a base, acid, base, I'll make that very clear, reacts to form 1 mole of water. This is already balanced, and sodium chloride is just a byproduct. So it needs to be so this one is already balanced. Whenever you're balancing it, you just need to make sure you have 1 mole of water being formed, okay? And to denote this, we say enthalpy change of neutralization, and it's minus 57, right? And I'll tell you something actually, something a bit different. So for the others, they had different values depending on the exact reaction occurring. For this one, it's pretty much always minus 57. So it's the exact value somewhere between minus 57 and minus 58. So negative because it's an exothermic reaction, okay? Why is it always this number? Well, what's really occurring here is it's just the reaction of the proton, so H plus, and the base, and that's reacting to form water, and it's 1 single mole of water. So whenever you have any equation that's formed 1 mole of water, and we've got an acid and base, it's always going to be protons reacting with bases, yeah, and therefore it's always going to have the same enthalpy. So it doesn't matter if it's sulfuric acid or any other sort of acid. It's the basic thing is that it's protons reacting with bases, acid reacting with base to form 1 mole of water. Therefore, the enthalpy change is always the same for all neutralization reactions. Okay, and that's pretty much it. Our intro on enthalpy, and I hope it all makes more sense to you now. Please like the video, subscribe, and you can check out our website for more video resources, www.jctuition.net. All right.